Hello, everyone. So today we're gonna look to finally finish up this section 4, notebook number 4. Just a second, sorry. And then we're gonna look at this concepts, all of this stochastic gradient descent, blah blah blah, and the little under the hood stuff that we did over the past couple of streams, and see, look at our dog classifier problem, the highly abstracted version of the project that we did earlier, and then figure out whether we understand some things better or just try to make this connection between what's happening actually, maybe with this perspective of the stuff that we learned before. That's the plan for today. And we should, however, start by finishing off the notebook we did last time, because we both kind of ran out of brain steam towards the end.
Yeah.
So, and for me, there wasn't much left, and I know there was a little left in the notebook. So we should probably get to that first.
Let's do
it. What
it.
do you think?
Yeah. Let's do it.
Okay, let me load up that, because I have one notebook loaded up, but not the right one. So I'm doing that now. MNIST, so we got a little left on MNIST. It's basics. And I'm going to share my screen again. Scream. Couldn't preview file. Yeah, sure. I want to open it. Collapse. All right, here we go. So we have the right runtime. Yes, connect. While I set this up, Nick, I have some personally exciting news, which is that I very recently had the great grand revelation that my old MacBook Air that I'm working on, which is the 2013 model, has, no, 2014, I think, or something, maybe 2013, who knows. I've had it for a while, and it doesn't have a lot of storage space. So I kept running out of storage, and recently I realized that I have a SD card slot. Did I tell you this already?
You did.
I got it, yeah. And I realized that there's an SD card slot where I could just essentially very easily double or triple or whatever nthify my storage in there.
So SD, you mean like micro SD?
I mean actual SD, like the big ones, but obviously I can.
And it fits. And it fits flush with the computer.
So there's some converter SD card thingies that make it fit pretty flush. Like not all the way, it's sticking out. I got it yesterday, and it's sticking out like maybe 3 millimeters or something like that. It's not much in the way.
Interesting. Okay.
And now suddenly I have, instead of just 128 gigabytes, I have the double amount for what cost me like, I don't know, $20 or something. Pretty exciting. So wait, there's a lot to run. Maybe I should do this differently, huh? Maybe we don't actually need to run anything because we're just reading about stuff, huh? We were putting it all together, we did that, and then we were looking at adding a nonlinearity. It looks like we're still running some code. So I haven't experimented much with having this new resource of feelingly unlimited storage, but it's exciting.
So what's the largest SD card that you can fit in the computer?
You mean storage-wise?
Yeah, storage-wise.
It just depends on how big the SD card is, right? And I've seen some that go up to a gigabyte. No, wait, terabyte.
Whoa, look out, everybody. 1 gigabyte.
Yeah, I wasn't going that crazy.
I do remember when a gigabyte, like for the, what was it, like old PlayStation, the game consoles? It was, I had a memory slot, and I think it was 32 megabytes to save your spot in the game.
Uh-huh.
And also for the, I had a PSP, the PlayStation Portable, and I remember those were also, it was like a weird SD card. It wasn't like the same format, like a physical format of an SD card. It was like, I guess Sony's proprietary something. And that was also like, maybe, I remember it being like some weird number, like 50 something megabytes.
50?
Yeah, like 550 something. Like it was weird because it wasn't like 32, 64 or anything. It was,
Interesting.
it was like 50 something, I remember. I could be misremembering, but it was definitely a megabyte in the megabytes, not gigabytes. So you could put so much stuff in your 1 gigabyte SD card.
It's true. But imagine I actually have a 128 gigabyte. No, so I'm thinking about installing some Windows on there because I need it for some programs. But I haven't gotten to doing that yet.
Can you boot up from an SD card?
Yeah, you can trick it.
I imagine the read and write is probably pretty slow through SD, no? Compared to your hard
like
drive?
I think so the stuff I read up on, it said it goes like some SD cards limited to 10 megabits per second, I believe. I might be messing up the things again with gigabits. I don't think so though. But the better ones do 20, which supposedly is similar to what like something that's built into the computer does. At least if your computer is as old as mine, I guess. I don't know what they're running with today. I'm just expanding all of these things to see where it's currently running, but it seems like it's going everywhere.
So the fastest SD card I'm seeing is the SanDisk Extreme Pro, and that's
what you just googled fastest SD card, or?
I just googled SD card speed,
and they got a speed comparison.
And this one is 275 megabits.
275? That's pretty fast.
I think it's got to be.
So what does
megabytes or megabits? I don't know. It's a capital B. I think it's megabytes. No,
I think they're doing in megabits.
Bits, yeah.
I'm expecting mine to do 20, just to say. And it probably also depends on the SD card slot or whatever. Like my computer has USB 2, so I think it goes at the speed of USB, maybe.
And you don't want to just get like a external
new
hard drive?
Computer?
Or like a new computer?
No, external hard drives are super annoying. That's the nice thing, is that it's just flashing there.
Yeah. I guess it's nice because like the SD card is also, it is flash memory versus like a spinning disk, unless you get like an SSD or something. But yeah, why don't you get a new? How old is your computer? 2012, 2011?
I think it's 2013 model, and I got it in 2014 as a used computer. So it's been doing a great job. I'm pretty proud of it.
Yeah.
Can't complain. But now there's new Macs out. And I mean, I was considering switching to Linux, but now there's a fancy new chip that for some reason doesn't even make the computer much more expensive. So
have you looked into, I haven't looked into the new Intel Macs, but everyone prior to
I
the
think
event,
it's past Intel, right? They're not doing Intel anymore. The thing is that they're making their own chips now.
Right. They're their own chips. Have you looked into it at all?
No. But I've heard people say it some GPU support actually. Like it does some, I don't know exactly how, but it seems like it does some threading, or it's got chip's got some GPU functionality built in, I think. So there's something about these computers are actually kind of useful. I mean, not like a real GPU, I assume, but that they're kind of actually useful for doing machine learning stuff. I don't know, desktop machine learning, you know, crazy world, but something like that, I believe.
I think some like the machine learning stuff though, you need. This is what was it, like Jeremy was saying about NVIDIA GPUs. So I think like a lot of this, a lot of these libraries and drivers are written for NVIDIA GPUs. So even if there are these like Mac chips, or the Apple chips, I don't think it
might need something else.
It's gonna be a while. Well, maybe.
Yeah, I mean, this is just a tiny chip, right? I'm sure it's not comparable to an actual GPU thingy, but something about it. I haven't read up on it, so this is just very layman blah blah, pulling it out of my behind, so to say. but anyways, I got more room in my computer. Exciting. And this is done, so we can actually start.
All right, let's do it.
All right, so last time we understood everything we read about, which was putting it all together. And the last bit we're missing now is adding a nonlinearity. All right. You wanna get going on that?
Sure. Oops.
And I reserve the power of scroll.
Okay. You're reserving the power of scroll?
Mm-hmm.
Is that what we said? Okay, so I'm not going to even request. All right. Adding nonlinearity. All right. So far, we have a general procedure for optimizing the parameters of a function. We have tried it out on a very boring function, a simple linear classifier. The linear classifier is very constrained in terms of what it can do. To make it more complex and be able to handle more tasks, we need to add something nonlinear between two linear classifiers. This is what gives us a neural network. Here is the entire definition of a basic neural network.
Oh, okay, let's see if we can understand this, huh?
Okay.
So we learned this is matrix multiplication.
Yes.
Right? Or multiplication. I don't know. I think it's multiplication. Was it? Or just matrix combination? Bias and weights. The original bias. No, what's that? What's XP? That's just right. It's just the images or whatever. That's the data.
Right. The images multiplied by the weights plus the bias.
Plus the bias. Okay. That's normal. That's the linear part.
Right. Which is also below the linear part.
Right.
And then res max.
Okay.
So what is
res
this?
max.
Tensor 0. So what is it? Getting the maximum value?
Not sure.
What is this tensor? So tensor function.
Def tensor device, like touch as tensor. This is it's just saying it's making a tensor out of 0.0.
Okay.
Yeah, no idea. Let's see.
Okay. So all we have in SimpleNet is two linear classifiers with a max function between them. Okay. Here W1 and W2 are weight tensors, and B1 and B2 are bias tensors. That is parameters that are initially randomly initialized, just like we did in the previous section. So W1, okay. Got it. The key point about this is that W1 has 30 output activations, which means that W2 must have 30 input activations, so they match. That means that the first layer can construct 30 different features, each representing some different mix of pixels. You can change that 30 to anything you like to make the model more or less complex. The little function res.maxTensor00 is called a rectified linear unit, also known as ReLU.
Like this before. Relu.
Relu.
Let's call it like that.
Also known as Relu.
Relu.
We think we can all agree that rectified linear unit, or Relu, sounds pretty fancy and complicated. It does. Relu sounds fancy.
It sounds fancy, yeah.
Not so much complicated, but definitely fancy. But actually, there's nothing more to it than res.maxTensor 0. In other words, replace every negative number with a 0. This tiny function is also available in PyTorch as frelu.
So res.max and then tensor, that it replaces every negative number with a 0? How would I know this from that code? Is there any mathematical?
I wouldn't know that either.
Okay.
This is why we don't assume things here. We've learned that from the beginning.
We just read.
Yeah. All right. So, I mean, I guess if you run that, you're going to get the same thing. Because we haven't done anything different. Or maybe you'll do. Maybe something different. Nope. Same.
Straight up. So there's no negative values, and
it looks like it's just going up one by one.
Mm-hmm.
Slope of 1.
Okay. Yeah, like 0.1, I guess, right? Or
no,
1.
No, it's 1. If you go, 2 is the same as 2, I think.
So it's got maybe 2 items.
Cool. So there's an enormous amount of jargon in deep learning, including terms like rectified linear unit. The vast majority of this jargon is no more complicated than can be implemented in a short line of code, as we saw in this example. The reality is that for academics to get their papers published, they need to make them sound as impressive and sophisticated as possible. Ooh, Jeremy opening the doors on academic papers. One of the ways that they can do this, they do that, is to introduce jargon. Unfortunately, this has the result that the fields end up becoming far more intimidating and difficult to get into than it should be. You do have to learn the jargon because otherwise papers and tutorials are not going to mean much to you. But that doesn't mean you have to find the jargon intimidating. Just remember, when you come across a word or phrase that you haven't seen before, it will almost certainly turn to be referring to a very simple concept.
Hey. What?
I'm going to use this pop filter because I keep hearing stuff in my voice, and maybe this will. Anyway, continue.
There's stuff in your voice.
It's like
the basic idea, or the basic idea, because it's the idea, but
it could be the idea.
The base, the idea.
Tomato.
The basic idea is that by using more linear layers, we can have our model do more computation and therefore model more complex functions. There's no point just putting one linear layer directly after another one, because when we multiply things together and then add them up multiple times, they could be replaced by multiplying different things together and adding them up just once. That is to say, a series of any number of linear layers in a row can be replaced with a single layer with a different set of parameters. But if you put a nonlinear function between them, such as max, then this is no longer true. Now each linear layer is actually somewhat decoupled from the other ones and can do its own useful work. The max function is particularly interesting because it operates as a simple if statement. If value is negative, replace with 0.0, maybe. Mathematically, we say the composition of two linear functions is another linear function. The composition of two linear functions is another linear function. So we can stack as many linear classifiers as we want on top of each other, and without nonlinear functions between them, it will just be the same as one linear classifier. Interesting. Amazingly enough, it can be mathematically proven that this little function can solve any computable problem to any arbitrarily high level of accuracy, if you can find the right parameters for W1 and W2, and if you can make these matrices big enough. For any arbitrary wiggly function, we can approximate it as a bunch of lines joined together. That's it, joined together. To make it closer to the wiggly function, we just have to use shorter lines. Yeah. This is known as the universal approximation theorem. The 3 lines of code that we have here are known as layers. The first and third are known as linear layers, and the second line of code is known variously as a nonlinearity or activation function. Activation function. Yes, also a term I've heard.
Mm-hmm.
Just like in the previous section, we can replace this code with something a bit simpler by taking advantage of PyTorch. What's this code? Which code? This wasn't such a complicated piece of code, huh? All right, anyways, I'm just scrolling around. So SimpleNet, NN, what was NN?
Maybe
Module torch.nn.
neural network.
Yeah, that makes sense. So SimpleNet, nn.sequential. Just in okay. So PyTorch has a torch.nn, yeah, neural network. Neural network sequential, so we're making a linear function here. No, sequential. Okay, sequential seems to be a class that allows us to combine the different types of functions. Right. Then we make a linear one. Rectified, what was it? Rectified, rectified. Sorry, I just want to know what this is called.
Was it rectified? I thought it was something else. Oh yeah, rectified linear unit.
Linear unit, okay. Rectified linear, because we're rectifying it. We don't want it to be negative, so we got to rectify it. And we rectify it to be linear unit above 0. I'm just trying to build myself some bridges in the brain. Okay, relu is a rectified linear unit, meaning everything that was negative was changed to 0. And then we're adding on another linear function after it. 30, what was that about? So that was the images input, like the size of pixels. 30 was arbitrary. There was just how many weights we want to do. And then what is this about?
So
31.
one was 30. So it was the inputs and the outputs. So the outputs and the inputs just need to match. So you could change the 30 to whatever you want.
Right.
They
okay.
just
so
have to be the same.
Match.
Yeah. So and in sequential, just what is this? Is this? Oh, it's setting it as SimpleNet. So it's taking all of these linear functions, and now
and the nonlinear one.
What was that?
And the nonlinear one. So everything, the linear functions and
Right. Okay. Creates a so, and then sequential creates a module that will call each of the listed layers or functions in turn. So that's all it's doing.
Yeah, I think so. And let me see if I can understand this. So the linear function takes as input. What was it? The 30 was just a number of, it said it was a number of different weights that it wants to look.
Scroll up a little bit. Let's just hammer that one in because it was.
Where was that? I think here. Okay, right so there, the key.
The first layer can construct 30 different features, each representing some different mix of pixels. You can change the 30 to be more complex. Okay, but before that, so the key point about this is that W1 has 30 output activations. So the first one, that 30 is the output, and then the second one is 30 input activations. Okay.
So this is a bit interesting. Like, what exactly does that mean? That it can construct 30 different features? Well, okay. I mean, I kind of get it. Like, I'm thinking of the image that we saw sometime earlier in the course, where it was like, look, this feature is recognizing all lines, or this feature is recognizing patterns like that, or something. Yeah. So something like that. I guess don't exactly get it, but. Okay, and then the connection is this output and input is the same, and the final one just gives us one output, is what it's telling us essentially, right? Syntax. Okay, cool, that makes sense. So the first one takes as input all the pixels, 28 times 28. All pixels of one image outputs 30 features. The next one takes in 30 features as input and outputs one final classification, essentially.
Yeah, that's what it seems like. But
cool.
Go down to the next. Was it also 30,1 in the?
In the one above?
No, in the one below.
That's the one below.
That is the one below.
Yeah.
Okay.
Okay, cool.
Cool. So nn.relu is a PyTorch module that does exactly the same thing as the f.relu function. Most functions that can appear in a model also have identical forms that are modules. Generally, it's just a case of replacing f with nn and changing the capitalization. When using nn sequential, PyTorch requires us to use the module version. Since modules are classes, we have to instantiate them, which is why you see nn.relu capital in this example.
Fair enough.
Because we can get its parameters, which return a list of all the parameters, modules. Let's try it out. Okay, whatever. Now we'll use a. Okay, so interesting. So let's try this out. As this is a deeper model, we'll use a lower learning rate and a few more epochs.
So how is it the deeper? So learn our data loader is SimpleNet. So we have these three, like two linear functions, one ReLU, optimization function using stochastic gradient loss function and MNIST loss that we defined earlier. Okay, matrix batch accuracy. Okay, so this is the, I guess, neural net that no, this is the neural net. This is the learner. Okay, whatever. Learn.fit. Let's see what you do. You get an attribute error. Great. Function object has an attribute parameters. Bam! Return p for p in m.parameters if p requires gradient. Interesting. Did we change anything? What could that? It could relate to the MNIST loss. That's the one that we defined ourselves, and the data loader, I believe. SimpleNet. Did I run this? I did not run this. Of course you can't do it if I don't run you. All right. Okay, so now we got this. Might take a little longer, I guess. No, it doesn't look like it. Look at all these epochs. Fun stuff. We are got 20, no more than 39.
So I'm just
going
to
define that.
I'm just muting myself to reconfigure the mic because it blocks the entire screen and I can't read.
Yeah, I shall audio relay to you what's going on. Learn.fit. So I don't know. We were just like defining that this is going to be for the epochs and at a learning rate of 0.1. And it started with an accuracy of 50%, went up to 80 right away, and then third epoch was already 0.91. And then we kept going up slowly. We broke into 98 at the 22nd epoch, and then stayed there until 39, going up 98. How much was that? 9808 was at 22, and then we went all the way to 9833. Yeah, we're not showing the 40 lines of output here to save room. We are showing them because I got a new SD card. So much space.
So now you can do it.
It doesn't have anything to do with each other.
Nice.
Whatever. The training process is recorded in learn.recorder with the table of output stored in the values output. So we can plot the accuracy over training as plot. Make one of these funky lists, learn.recorder.values item got 2. I don't know what the item got 2 means at all. I'll give it one try. Maybe that's got nothing to do with it, and it's some matplotlib stuff. Oh, that would also work. Let's see. Unexpected enough file. Expect to close a bracket somewhere. Yes, these are 2 brackets. Got something for us. A nice type error. Beautiful. String not method. Because this is passing something. Plot. I don't actually want to plot it. I just want to know what item got does. So, but this we're calling it on the plot object, it seems. It would be nice if there was like a right click or something. So if that works, probably not because I'm calling it. Non-type object has an attribute name because it seems that this doesn't return anything. What do I have to call it on? Plot. Ah, we're actually plotting here, so this is fine. I can get rid of that. And then should work. Yes, there we are. Okay. Create a new list with item index of all items. Item index of all. So we're passing 2 to that item got. So the index is 2 that all of the items should have. What does that mean? We're plotting the learner, the values, and we're making a new list out of this where the item index 2 with item index of all items. For all items with 2 items for each item that's in there. Is that what we're saying? Interesting. Okay, I don't really get it. What happens if I try that? That shouldn't be out of range. Completely different curve. So strange. What happens if we don't do this? Are you back with the audio?
Yep. Yeah.
Oh, look at that.
Oh, wow.
Those are the, so we get the values. Is that, do you think those are the curves showing?
So scroll up a
Maybe
little
they're
bit.
lost.
Are we finished training?
Yeah. This is already, we're already working with the recorder is actually showing us it's showing us what the training did, like all of the different epochs are in the recorder.
Got it. Okay. We're not showing. So these are all the values.
These are all the values, and then I don't really understand what the item got does, but I also don't really understand what the recorder, like my understanding is this is just behaves like a list of items, but can also index with lists of indices and masks.
Yeah, it seems like the item got, 2 worked, 1 worked. I'm assuming 0 works because there's 3 lines on that graph.
Okay, so we're getting one of those lines. Nice, that makes sense.
That's what it seems like.
Yeah.
So 2 may be the green one, and then 1 and 0 may be the blue and the orange.
Let's try that. I'm just interested what does not support indexing. Didn't we just, but can also index with list of indices or masks. Okay, so we got item got, and we picked the second one.
And that should be the green one.
It should be the green one, but it's not going to be green if we just display one of them.
Right.
It's going to be blue. Okay, that makes sense. 0 should be one that's shaped the other way around. One of the bottom 2 ones, and 1 was the same, right?
It's going to look the same, shape, but it's similar, yeah.
But it starts at 40. So if we look at all of them again, we get? Okay. Yeah, it starts at 40, so this is 1, so this is 0, 1, and this is 2.
Cool.
Okay, so these are different. I wonder what they are though. Like, what is that?
Let's scroll down. Keep reading.
Okay, this indexing didn't work. I'm okay with that though.
Is that something that you put, or?
I did that, yeah.
Okay.
I was just in, because it said that you can index it, so I should try it indexing it, but it didn't work in that way that I was trying at least.
Got it. Okay.
Now we can view the final, so another indexing. Now you can index the values, maybe, not the recorder itself. And we can view the final accuracy, learn.recorder.values -1. So the last is the final accuracy. And then minus, so that's the last curve. That's probably the last, that's the last training, right? I mean, the last epoch probably. But that would mean we should have 40 values here. Am I misunderstanding?
Yeah, I don't know. Let's see. How many? Can you do the length of that?
Yeah, I'm trying. Okay, cool. Yeah. So we're getting the final, like the numbers of the final. But then let's just look at one of them. Let's look at the last one.
3. Okay, so that
3. It doesn't make any sense to me.
So I wasn't really paying attention, so I'm just gonna, like, with context clues, make some sort of assumptions. I think they're all gonna be 3, and I think the 3 is just, that is the value. So like 0.98 is the value where that's getting plotted on the graph. So if you scroll up, like if, okay, so hold on, actually let's do this. Go scroll down, and then just do 0, and then do another parentheses, get the first one.
But why would that print out as 3? Right, sure.
Because there's three graphs, there's 3 lines.
So
oh no, not the length, the actual value.
That's why I was printing 3. I forgot that I had the length function in there. Yeah, okay, that all, now everything makes sense to me. I was just confused why it was giving it 3.
Yeah, okay, I got you. Cool.
Okay, cool. Yeah, and so then here we said that this last one is the accuracy. No, that's 0, 1, 2. Yeah, so this is the accuracy, right? And that's the first item. I said that, like, it started off with 50% accuracy and then went up all the way up to 0.98.
Yeah, and then so if you scroll up to the plot, it should say that green line. Yeah, so it starts at about 50 and then ends very close to 1. Right, okay. Mm-hmm.
And then we have the other 2 values that are these 2, which are the loss
and the training loss. Yeah.
Training loss, right? Loss. Okay. So we see, nice. Okay. So we see the the losses both decrease over training time, and the accuracy goes up.
Yep.
Cool. Nice. At this point, we have something that is rather magical. 1. A function that can solve any problem to any level of accuracy, the neural network, given the correct set of parameters. 2. A way to find the best set of parameters for any function, stochastic gradient descent. This is why deep learning can do things which seem rather magical, such... What? This is why deep learning can do things which seem rather magical, such fantastic things. Wow. Such great. Such magic.
Such magic.
Wow. Believing that this combination of simple techniques can really solve any problem is one of the biggest steps that we can find many students have to take. It seems too good to be true. Surely things should be more difficult and complicated than this. Our recommendation, try it out. We just tried it on the MNIST dataset and we have seen the results. And since we're doing everything from scratch ourselves, except for calculating the gradients, you know that there is no special magic hiding behind the scenes. All right. Go deeper, Nick.
Going deeper. There's no need to stop at just 2 linear layers. We can add as many as we want as long as we add a non-linearity between each pair of linear layers. As you will learn, however, the deeper the model gets, the harder it is to optimize the parameters in practice. Later in this book, you will learn about some simple but brilliantly effective techniques for training deeper models. We already know that a single non-linearity with 2 linear layers is enough to approximate any function. So why would we use deeper models? The reason is performance. With a deeper model, that is one with more layers, we do not need to use as many parameters. It turns out that we can use similar matrices with more layers and get we can use smaller smaller matrices with more layers and get better results than we would get with larger matrices and few layers. Okay, so we don't need to use as many parameters. We can use smaller matrices with more layers. Interesting, okay. That means that
with the parameters, sorry, just a second. The parameters would be those 30 things that we had. 30, no, those were the output. Where did the parameters come in? Are the parameters the pixels?
The 28 by 28.
Yeah, so the pixels, okay.
That's what I think, yeah. Mm-hmm. So we get smaller matrices. And maybe this is why with more layers and get better results than larger matrices and few layers. So maybe this is also why in the beginning we were doing that like 128 by 128 image versus, I mean, also could be because Colab we're just burning through GPU if we use larger images as well. But that's just one thing that stuck out. All right, anyway, moving on. That means we can train the model more quickly and it will take up less memory. In the 1990s, researchers were so focused on the universal approximation theorem that very few were experimenting with more than one nonlinearity. This theoretical but not practical foundation held back the field for years. Wow. Some researchers, however, did experiment with deep models and eventually were able to show that these models could perform much better in practice. Eventually, theoretical results were developed which showed why this happened. Today, it is extremely unusual to find anybody using a neural network with just one linearity.
One non-linearity.
With one non-linearity.
Also just one linearity.
Oh, sure. Here's what happens when we train
I think those typos.
Yeah. When we train an 18-layer model using the same approach as we saw in open and close carrots. Side carrots.
Carrots.
In less than, greater than. Or sideways.
Okay, here's what happens.
Sideways excited. Sideways shocked.
True.
It looks like a sideways, like a shocked chicken or something, right? Like with the beak opening.
Yeah, let me zoom that in. Okay. Data load. We'll get here. Okay, we're making an image data loader from a folder path, from a folder. Learn, make a convolutional neural network. The ResNet pre-trained false pay loss function. F.cross entropy, because why not? Metrics equals accuracy. Okay. Learn fit one cycle. 0.1. 1, we do one epoch, 0.1 is the learning rate. Okay. So we train an 18-layer model, a ResNet 18, instead of the little neural network with 3 layers that we looked at before. Now here we're doing an 18-layer model. Interesting. So this is cool. So this little thing, where is it? Is the model. It's so far up. The scrolling is such tedious work. Where are you? Here, SimpleNet. Okay, nice. And then the ResNet 18 is just an 18-layer model, not a 3-layer model. And I'm sure it's got some smart stuff in there, like which activation functions to use and which linear stuff. But essentially, that's because that's what we're replacing here, right? Instead of running the little SimpleNet here, we're inputting the ResNet 18, and that means it's an 18-layer model. We're using a different loss function, I guess. Not the one that we defined manually up, but otherwise it's the same. And then we just train for one epoch. What do we get?
Very slow.
The tension is rising. There it is, it's starting.
How's is the phone charging, or is that 1%
it is
lasting an hour?
It's all right, it's charging. It's up 42. I managed to get it to charge.
Okay, good.
Wow, look at that. So we get a better accuracy with one epoch of training. Crazy. Just because it was deep.
Very interesting.
Uh-huh.
Okay, nearly 100% accuracy. That's a big difference compared to our simple neural net. Yeah, but as you'll learn in the remainder of this book, there are just a few little tricks you need to use to get such great results from scratch yourself. You already know the key foundational pieces. Of course, even once you know all the tricks, you'll nearly always want to work with the pre-built classes provided by PyTorch and fast.ai, because they save you having to think about all the little details yourself.
Nice. Congratulations.
Wow.
Confetti.
Yeah.
You now know how to create and train a deep neural network from scratch. We've gone through quite a few steps to get to this point, but you might be surprised at how simple it really is. I did get some understandings here that I didn't have before. It's nice. Now that we are at this point, it is a good opportunity to define and review some jargon and key concepts. A neural network contains a lot of numbers, but they are only of two types: numbers that are calculated and the parameters that these numbers are calculated from. This gives us the two most important pieces of jargon to learn: activations, numbers that are calculated both by linear and nonlinear layers; parameters, numbers that are randomly initialized and optimized. That is the numbers that define the model. Okay, so, and should I do some scrolling? No, this is too far. But the 30 in the first one was an activation, and in the was a parameter, randomly initialized. Now the weights are parameters. And the activations are what were the 30? We will often talk in this book about activations and parameters. Remember that they have very specific meaning. They are numbers. They are not abstract concepts, but they are actual specific numbers that are in your model. Part of becoming a good deep learning practitioner is getting used to the idea of actually looking at your activations and parameters and plotting them and testing whether they're behaving correctly. Our activations and parameters are all contained in tensors. These are simply regularly shaped arrays, for example, a matrix. Matrices have rows and columns. We call these the axes or dimensions. The number of dimensions of a tensor is its rank. There are some special tensors. Rank 0, scalar, which is a number. Rank 1, vector, which is a list, I guess. Rank 2, matrix, which is a table, if I want to give it different names, right? Rank 0 tensor, rank 1.
Yeah, for more or less.
A neural network contains a number of layers. Each layer is either linear or nonlinear. We generally alternate between these two kinds of layers in a neural network. Sometimes people refer to both a linear layer and its subsequent nonlinearity together as a single layer. Yes, this is confusing. Sometimes a nonlinearity is referred to as an activation function. Summarizes the key concepts related to SGT. Guess here is our...
Oh, this is the table. So like scroll down, does it actually, yeah, there you go.
That's part of this whole thingy here. So look, DL jargon 1, this is what happens inside of this. Below is a summary of the key concepts. Then I can do this. And term meaning. You will be very excited how beautiful this looks in just a bit. Whoop. And then I can do whoop, whoop. I just need to know where's the end of each of those. Whoop. Whoop. Don't mess with me. This is super annoying. This is the last time I did this too. It keeps jumping back. But we're already at the end. Ship. And beautiful, huh?
Beautiful.
So now we can review our terms. ReLU, rectified linear unit, is a function that returns 0 for negative numbers and doesn't change positive numbers. Nick.
Mini batch, a small group of inputs and labels gathered together into arrays. A gradient descent step is updated on this batch rather than a whole epoch. Martin.
I didn't quite get this actually.
It's actually a small group, not a small group. I was
small. Now everything makes sense.
Yeah. So a small group.
A
small group of inputs and labels gathered together into arrays.
Inputs and labels. Okay. I think now I get it. I don't know why I didn't get it before.
Martin.
Forward pass. Applying the model to some input and computing the predictions. Nick.
Loss. A value that represents how well or badly our model is doing. Martin.
Gradient. The derivative of the loss with respect to some parameter of the model. Yes.
Okay. Backward pass. Computing the gradients of the loss with respect to all model parameters. Yep.
Gradient descent, taking a step in the direction opposite to the gradients to make the model's parameters a little bit better.
And learning rate, the size of the step we take when applying SGD to update the parameters of the model.
Nice. So, and what about, can we go back to activations and parameters? Numbers that are calculated both by linear and nonlinear in layers. And parameters, numbers that are randomly. So parameters, the weights would be parameters because we're randomly initializing them at the beginning.
Yep.
And then we're optimizing them. And the activations are the layers, right? That come out like 30.
Yes, I believe so. That's how I'm understanding it as well.
Cool. Good. Note, choose your own adventure reminder. Did you choose to skip over chapters 2 and 3 in your excitement to peek under the hood? Well, here's a reminder to head back to chapter 2 now, because you're needing to know that stuff very soon. So this is what we're going to do. Wow, really, it's just good learning material. It's not us being great. Okay, anyway, oh, this is a lot. Oh my God. These are important though, huh?
I mean, is it? Can we just jump straight into the dog classifier, the dog breed
Yes.
classifier, and then just
And maybe if we feel like it, we can come back to the thing after.
Reconnect.
Yeah, I'm just gonna get rid of this one because we don't need it anymore. Bye. Did I disconnect? Random disconnected. Good. Freeing up some memory. And then we want to reconnect this one. Connected. Okay. So now we want to do. Is that already done? Anyways. You good? Or do you want me to connect again? Yes.
Mo, are you hiding your one-time authorization code?
We're still not entirely sure it's one time. I do think it is. Fun stuff is that it always shows it anyways once you enter it.
Right.
So, gotta scroll over it. I thought it would just be nice to show our faces a little. Here we go. And we're back. Getting Regs images. Okay, so I believe I cleaned this up in a way that we should actually be able to run it and it should work. So this is going to be the real life test whether I actually did a good job cleaning it. But
is this what you were cleaning in the other, like you did a whole cleaning video on this, right? That's what's on YouTube now? That's this?
That's this one, yeah.
Okay, cool. And you haven't run it yet?
No, I haven't. Testing, come on.
You just cleaned it. And you left it. You didn't even oh, wow.
I mean, I ran it while I was cleaning it. But
right.
Who knows what goes on there?
Right.
My drive data. So this already exists in here, dog breed classifier. We don't really need to download all of this stuff anymore, you know? So I'm wondering whether we should skip it. Make directory exists, okay, true. Okay, we should be able to run that without any problems. It's just,
cool.
It's creating it, or if it already exists, it's fine. So this is the couple of images from the Regs that I got from you. Dog their urls.txt. I mean, I already have this file, so I don't really need to make it. Check out the docs by running. Download images. We also have those already, but whatever. Download them again. Gathering the dataset. More elegant way to download an entire dataset using fast.ai. Okay, so this is still using wget, but we get the Stanford Vision.
So we already have this, right? We don't
dog
need to
breeds,
download this
got
again.
that. I don't need to write. Yeah, so let's just look at that. Yeah, everything's here still.
Cool.
And then we can double check. We can access the images. Vizsla. Here's a Vizsla for ya. Vizsla. Okay, so this is all, I mean, this doesn't have anything to do yet with fast.ai, so I'm just skipping over it because we're not really doing any deep learning.
So in no way or shape is this any sort of promotion, but last time we looked at this, we were like, the idea, like Vizsla, I don't know, like for some reason Vizsla came up like so many times. Like I was out with Regs and somebody came up to us and was like, is he a Vizsla? And I'm like, I don't even know what that is. And then we found out, and then now we're using Vizsla here. And I was just in Tennessee and we stopped at an REI and I bought a pair of like a bathing suit. And the brand was Vizsla. Like, I didn't even realize it. And then the other day I looked at it, and the label on it said Vizsla on it. Just a little fun.
What's going on with that?
It's not, it's spelled Vizzla, I think.
Spelled differently.
Yeah.
So it's just
so
the dog.
Cute.
These ZS, not SC. The Vizsla is a natural hunter endowed with an excellent nose and outstanding trainability. It was bred to work in fields, forests, or bodies of water. Although they are lively, gentle-mannered, demonstrably affectionate and sensitive, they are also fearless and possess a well-developed protective instinct.
What does Wikipedia say for Chesapeake Bay Retriever?
Okay, let's do a little bit. I'm not going to be able to write this. You got to spell it for me. Oh, I was able to spell it. Who would have thought? Chesapeake Bay Retriever is a large-sized breed of dog belonging to the Retriever, Gun Dog, and Sporting breed groups. Members of the breed may also be referred as Chessie, CBR, or Chesapeake. The breed was developed in the United States, Chesapeake Bay. Where is that?
In like Maryland area.
Okay. During the 19th century, historically used by area market hunters to retrieve waterfowl, pull fishing nets, and rescue fishermen. It is primarily a family pet and hunting companion. They are often known for their love of water and their ability to hunt. So maybe you should give him more baths. There's a medium to large sized dog.
He hates baths.
Well, maybe just let him jump into a lake or something like that.
Jumps into a lake, loves grabbing things, like so pulling fishing nets, which is kind of funny. We haven't actually tried that yet. I would love to throw like, so whenever I'm in the water, he does try to swim up to me. I wonder if I did have a little rope that he can tug on.
To pull you back to safety.
Back to safety.
That could be fun.
Yeah.
That could be fun. There's a wavy coat and a Labrador smooth coat. They are described as having a bright and happy disposition, courage, willingness to work, alertness, intelligence, and love of water as some of their characteristics.
We were recently talking about getting a so the weight on this, so that's why he's not like a true Chesapeake. He's definitely a mix because of the coat and the size. He's 45 pounds versus this like 75 to 100. Yeah, this much larger than Regs. So maybe we'll get like an actual DNA test for him.
Wait, you don't trust our classifier?
Well, to just compare to the results of the classifier.
Right, with traditional methods.
This is the validation.
Okay, I like that. Okay, sweet. So let's move on here. We have a folder with images. Still, this is just doing a pathlib. And then get image files. I guess we can start looking a bit deeper. This is a function that's implemented by fast.ai, I believe. Get image files. It takes a path, recursive true by default, and says that there's no folders. Folders none. I wonder what's that. Maybe you can define which folders to pick and which ones to not pick. And by default, it just takes all of them. Because we definitely have folders inside of images. There's all these nicely named ones.
Yeah.
Get image files and path. Only in folders like it is. Again, I just need to keep reading. Only in folders if specified. Not even far to read. It's like the tiniest.
The next line.
Iota of difference. Okay, so we get more if we look at docs. Get image files. Only in folders if specified. This is simply get files called with a list of standard image extensions. Okay, so you can take a look at get files. extensions none, recursive true, folders none, follow links true. Get all the files in path with optional extensions, optional with recurse, only in folders if specified. This is the most general way to grab a bunch of file names from disk. If you pass extensions, including the dot, then returned file names are filtered by that list. Only those files directly in path are included, unless you pass recurse, in which case all child folders are also searched recursively. Folders is an optional list of directories to limit the search to. Seems all pretty straightforward. .jpeg, and then get image files is probably his JPEG, PNG, and all of that stuff in extensions. It's often useful to be able to create functions with customized behavior. Fast.ai data generally uses functions named as camel case verbs ending in -er to create these functions. File getter is a simple example of such a function creator. Wait, this is to create functions with customized behavior. Generally uses functions named as camel case verbs ending in -er to create these functions. So file getter is a function that creates a get files function that searches paths of only in folders of specified. Why would I do that? Why would I not just call this function get files and pass it to extensions? Do you understand? Is that something that Go does?
I've seen this before, where creates a get files partial function that searches path suffix only in folders.
Okay, I get it. Okay. So I think the idea is that, so you don't want to, maybe if you call this function, that's the replacement for get files, right? But you would always have to give all the inputs, right? So extensions, maybe you want to search only for PNG, then you can use this file getter to essentially set this extensions for all of the ones that you want to use later. And then you only need to pass the argument that the parameter that you actually want to change.
Right.
Okay. Oh, yeah, and here, like, you want to change this because here that you change the default. I see. Interesting.
Yeah, no, what's interesting, so when you said that, there's a similar whatever, forget it. I was gonna say there's something similar like this in Go, but it's with like interfaces and it's something different. It's like using the camel case verbs, and then the ER is you add that to like an interface if you wanted to create an interface for like something like this, like file getter, or this doesn't make any sense because file is not a verb but get is a verb, so it would be like read writer. So anything that implements a read function and a write function inherently is part of this interface. It's interesting.
Okay.
You will be the first one to review that, as you are reviewing my Go course.
I mean, read over it today already.
Yeah. Well, after I clean up a few things.
High level.
Yeah.
Okay, so cool. We dove a little deeper under this. Get image files actually implements get files with a couple of custom extensions. And we have the default settings. We want to use all of the folders and go recursively. So we just need to put in the path, which is the path to the images directory that contains all of them. Pretty cool. I added it was Jeremy. I just love working in Jupyter notebooks, and I put in a little and Martin. We both love it.
It's cute.
Okay, so next one, verify images. What's going on in here? Okay, find image in Finesse. Verify images. Find images in fins that can't be opened. Excuse me, Finesse, what would that be? Functions, no. File name, file names, right?
Yeah.
I don't know. I'm just guessing. No, you're just laughing at me.
Well, like I like it could be called anything, right? Like it could be called pancakes, right? It doesn't really matter. Isn't that just like the parameter of?
Yes, but I'm wondering why. Okay, so you just pass it in a bunch of a bunch of paths, I guess, which is what we should have gotten from this. Get image files, and we saved it as file names because it's actually just paths. Okay, and then we're passing these file name paths in there, and it tries to open each of them. If it can't open it, then it adds it to this list. In this case, all of them could be opened. And then we could failed.map, look at unlinked. Okay, we're still not really, okay, now data loaders. It's maybe a bit more in the territory of the stuff we just read about. Data block. What's a data block? Source. I think it's different.
What do you
That's the source code. I'm just diving deeper into these pieces that we're using in here. Any suggestions, or you don't like that? I thought that was our plan. No, did I misunderstand?
No. This is
Give
fine.
it to me.
No. I thought no. This is fine, and it's good because we're getting a better understanding of like breaking each individual piece. I think in the last episode, what I meant was breaking away some of the learning abstractions. So like where it starts learning, we replaced those fast AI functions with the functions with manual. The manual functions. Okay. But we'll eventually get to that because I don't think this is super long. I think we're going to load the data and then we're going to learn right after.
Right. Yeah, we're pretty
shortly. So this is
showing batch.
Yeah.
I think we still do, like this.
I think we still have to
potentially
do that.
A couple of rabbit holes here. We can also skip it if we want to try this other stuff. Okay, this is where we start training, which arguably is the thing that we read about before. So let's look at what a data block is, because I feel like that's pretty important. And then I'm happy to jump to the training.
Let's do it.
Okay. It is a generic container to quickly build datasets and data loaders. What's a dataset, Nick?
A set of data.
Yeah, but how was it defined in our last thing that we did, last stream?
How was it defined? Oh, was that the
two
tensors, one with something and the other one with, or one was, I don't remember, one was something and the other one was with the labels, I think, or some sort of validation.
It was
tuples.
Is it tuple?
Two tuples.
It was it was one tuple consisting of the data and the labels.
Right.
Like
it was
a
one
tuple of two tensors.
Yeah. Okay, that's what it was. A tuple of two tensors.
One of them wasn't even a tensor, I believe.
One was a tensor and the other one was a tuple.
Right. Yeah. So a tuple of a tensor and a tuple.
Tuple of a tensor and a tuple.
Right. I think.
Tuple of a tensor and a tuple.
Or maybe not.
It sounds like a cool like restaurant or like a little coffee shop or something. Tuple of a tensor of a tuple.
Of a tensor of a tuple?
Yeah. Or like a children's book. It flows off of the tongue nicely. It's got this like nice rhythmic way of you know what I mean? Did you freeze? You're back.
It's going crazy.
I don't know what you're hearing, but anyway, tuple of a tensor of a tuple.
Nice back. It just wanted to censor your ideas for me, it seems.
Well, the rest of the world got them.
That's good. So at least if it's plagiarized, it wasn't me.
Right.
Or was it? Did I hear it?
I don't know.
Did I watch the stream?
Well, this is episode 9, so you will be timestamping this one as you are doing odds.
Ooh. Maybe we should wrap it up. I think we did enough for today.
No. We're just getting started.
No.
We have another hour and a half. No.
Damn.
All right. So the data loaders, data loaders. So how do we feel about data blocks?
I'm partial to them.
I'm partial also, only because we've only gone over the data set part of it and not the data loader part. And the data set we know is a tuple of a tensor of a tuple.
Right. Data loader sounds a little more complicated. Huh?
It just sounds like it's loading data, to be honest. It doesn't sound like it's doing anything.
Such a weird syntax. Get x equals get items equals splitter equals get y equals none. Such an interesting way of initializing all of them to one variable, I assume.
So I guess the other way of doing it would be like commas throughout, but then you would have to say none, right?
Yeah. I'm not familiar with the syntax. It's interesting. Blocks, data loader type. Like here he's doing that, right? Here's initializing blocks to this first tuple.
Sure, but those are two different things, yeah.
And then, yeah. Get items splitter, get y, get x dot split. Oh wow, that's very strange programming, Python programming. So here he's using a string and splitting it up.
Seem like
in the spaces to get the names for the methods that he's probably using later.
It's
so weird.
It's interesting, yeah. I've never seen this like this.
It feels kind of dirty, but who cares, right? I mean, it works.
It does.
You wanted to call several transforms in your getter. Don't forget to wrap them in a pipeline message. That's our message, okay? Initialize self blocks none, data loader type none, getters, blah, blah, blah. Lists.
Does the underscore, like the prepending underscore, does that mean anything in Python?
Yeah, it's like, it's kind of telling you that these are private attributes. They're not really, like you can, but you're not supposed to change them essentially. It's like an indication for the user to leave them alone.
Got it, okay.
And then you have this double underscores, which is another, like, a deeper level of privacy essentially. Those are the internals, don't mess with it essentially.
Sure.
That's what it's saying.
But like the Python interpreter understands double underscores.
How do you mean?
It uses the double underscores, right? So I remember like when you're defining
it's just
main,
normal
it
characters.
like looks for it. The init, like that means something in the Python interpreter. Like when your program is running, no?
The double under main, you mean? I think that's just the name of the module that you're running. It's called a main.
So could I change the double underscore main to not have double underscores?
Yeah, but you'd have to change it with the internals.
Right, okay, so it is the internals of Python that interpret the double underscores with some sort of meaning.
Yeah.
Okay.
I mean, again, like for a class, in this case, the init function double under init is like the one that creates an instance of the class. So if you use this, if you write data block and then put in the brackets, if you call an instance, if you create an instance, then this is what gets run, the init function method in here.
Right. Yeah, I think that answers my question. Like Python, so on 91, combine type TFMS, Python doesn't run that automatically. It only runs the init function by itself. So only double underscores prepending and prepended.
And also those don't necessarily run by themselves.
Well, the init one, for example.
The init one does, but yeah. You can like overload stuff like additions, like the addition operator, the plus, you can overload with a double under add, and then that knows that it connects to the plus and stuff like that.
Okay, cool.
Okay, yeah, this is too much code, huh? Another day, maybe. Class data block. Generic container to quickly build datasets and data loaders. To build a data block, you need to give the library 4 things. Sugar and rice, type of your input labels, and at least 2 functions, get items and splitter. You may also need to include getX and getY, or a more generic list of getters that are applied to the results of get items. Once those are provided, you automatically get a datasets or a data loaders. Get a datasets or a data loaders. Okay. We would like to do that. Then we're applying some transformation. The training set. Do we do anything in here? Apply the augmentation. Okay, item transform. This is the thing that we said to apply. The docs.data loaders path. Not sure what that does. Do you want to dive or? Now we're here. We made it by me just skipping.
Are we everything?
We're here. We have arrived.
We've arrived.
We have arrived. Welcome. It is now time to drizzle apart the. So what do you want? So you're thinking about what can we do? We're not going to change the data loader, right?
No. Can you go back to the MNIST?
Could build a different ResNet. Like we could build our own net.
Well, hold on. Go back to the other tab. Yeah.
Whereabouts?
We're right there for a second. So we train 18-layer model. Okay, so this is literally the same thing, but just using a different cross entropy versus where I think we're using something else.
I don't think we're even using a loss function. That wouldn't make sense.
We're not, yeah.
But that's weird, right? Shouldn't we always need a loss function so we know whether we're getting better or not?
It could be that there's one that's like a default one predefined or something.
That it always applies if you don't specify it. Yeah.
So I guess what we could do is why don't we first let's apply a loss function to this. So this was already run. I guess you can run this again and you'll get the same training loss and valid loss and error rates and all that. And then if we apply the loss function, we can see some of the differences, just to get a better understanding of what's happening.
Sure, let's do that.
And then
let's use this one, cross entropy. Why not?
So one thing though, learn.fineTune for, I don't remember what fine tune is. Is that the loss function?
No. So fit one cycle. What did we do when we did the 40? Let me just double check that.
So mnist loss.
Learn.fit. So it's not fine-tuned, but we're doing learn.fit.
Right, that's just saying we need 40 epochs.
With a learning rate, yeah, but no, I'm just looking at, it's different types of actually training the model. And we used, in this one, we used .fit, we used fit one cycle, and here we're using fine-tune.
Right, so that's what
could
I'm
also
saying.
try
maybe
seeing what's the difference between those.
Yeah, maybe fine-tune is applying some sort of like, I don't know, loss functions or optimization functions on there. Because on the other mnist one, there's a loss function and the optimization function. So we have SGD plus the mnist loss. We didn't go over this entropy function that we're planning on doing. And we wouldn't use the mnist loss anyway, because that doesn't make any sense.
No, yeah, that doesn't make sense.
So where did we define mnist?
So I'm just moving this here so that we have them together. Oops. Your internet connection is more stable. Do you need the phone?
Can you put it like...
Just a second. Wait, Nick, I'm just gonna figure out the internet for a second.
Sure.
No, I'm just asking if you can try putting it there. So it's more...
Let's see. It was really low on power. You hear me again?
Yep.
Okay, cool. Just the internet being slow. We have 2 calls going. It's a bit too much. All right, let's see. Okay, so I wanted to move this down here. There we are. Matrix patch accuracy, and then we ran this one with doing learn.fit, I believe. And did we pass it anything?
Yeah, it was 40.
40 and 0.1. So that was the learning, that was the epochs and the learning rate, right?
Yep.
Okay. So, and here again, epochs learning rate, but we're using fit one cycle, which seems, I would assume it already just does one epoch. Not sure though.
You hear Regs?
Yes, I do. Yowling. Okay, so let's try running. Let's just try.
The sounds of Brooklyn. Okay, so let's try doing. So this is learn.fineTune. What did we train? Okay, so we're adding a cross entropy loss function, and let's do.
And also an optimization function, right?
Sure, why not?
Yeah, maybe we can try without it later, but let's start with this. Loss function. So we're adding this, and we're adding this. Resonate 18, we get metrics. Okay. Data loaders, resonate 18, metrics, error rate, loss function, cross entropy, optimization function, SGD, and then learn.fit. And we gotta give it a learning rate. So let's say 0.1.
Sure.
Okay.
Yep.
And then let's see what's the difference. I'm gonna start this because I think they're gonna take a while to run since we're running through all of those images.
No, this one I think was supposed to. Oh.
This has a bunch of
yeah,
different dog breed images. Yeah.
Yep.
So this is it's gonna take a bit. Okay, so and then in the meantime we can build the next one where we're gonna use fit one cycle.
Well, I think we should still have this like.
You don't want to do that one?
I do. I just want to keep the one that was originally there, so we can.
Yeah, we still
can do the comparison.
we don't have.
Yeah.
You're
just
right.
make a copy of that one.
Yeah, we should keep that one around, right? Senior learners, and then we do a fit one cycle, present one for the epochs, and then a learning rate again. And then what do we have up here? Resonate pre-trained equals false. Loss function.
So
cross entropy.
Okay, so just the pre-trained and the loss function, and
they're using a different metric too, actually, but we're gonna stick with our metric, huh? Over here.
Yes.
Good idea. Bad idea. Who knows?
Well, we could. I mean, we could do both. It's just gonna take a while.
Yeah, it takes. I'm not sure that maybe we should choose a different project for that. Actually, if we're playing around like this, especially because we're running on 4 epochs. We could also just do fewer epochs, I guess. But even then, it still seems to be taking a while. Wait, just double checking. I'm pretty sure we're on a GPU, but yes, just making sure.
Ooh, the RAM is. We're probably gonna go to that again. I think we're gonna run out of memory soon. Oh no, never mind. I thought it was
used. Yeah.
Yeah.
It's not. Yeah, different. Yeah, we're still fine.
Mm-hmm. No, just seeing the RAM and the GPU next to each other. I thought it was 3 point whatever out of 3 point something. I'm like, ooh. Maybe we shouldn't have printed those mutations.
Okay, so yeah, we can't really do anything here. We gotta wait for this to finish, which is gonna be a while. So let's see what we understand about it.
So I think let's take this first one, the one that's running right now, and break it up. So we have the metrics, we're still doing the error rate, and the loss function, cross entropy, and the optimization function is SGD. So let's go back into the other notebook and scroll up, and then let's see how we're defining these functions and how we're using them a bit further, because I remember like all of this text down there is like, well, we did it for you, so like now you understand it. And you know, I remember seeing that last time.
How far do you want to try looking for it? Because I'm not sure what you.
It was like almost to the top. I could
okay.
scroll.
Are you sure? Because this is really far. This goes far up.
Yeah, it was in the not the SGD one, the one right after, the one we did last time.
SGD is what we did last time. The one before that?
No. Scroll down a little bit.
MNIST loss?
Yeah, MNIST loss
Okay,
function.
you're right. That's what we did last time. Where are you? Okay. Relu.
Okay, so
You got anything? I'm happy to give you remote control if you want to scroll,
sure.
because maybe you know what you're looking for better. Right.
Okay. So here, we'll concatenate them into a single tensor and also change them from a list of matrices to a list of vectors. Okay. So here we're data set PyTorch required tuple. Ooh. So what I was thinking is
Speak your mind.
what is a stacked threes? Or maybe it was here that we started doing. So I guess what I'm looking for is somewhere we defined these. I don't remember if it was the loss function or the optimization function, but we defined them somewhere.
Lost that backward. Maybe you're getting there. Wait. There was you were just using the loss function, so maybe if you go a bit further up, there's a definition of it. Bless you.
Thank you.
You were fast with the mic on that one. Nice job.
I felt it. I felt it coming, and I'm like, oh, I need to loss. Okay, loss dot backward. But I think the backward.
Loss MSE. Look, there it is. There it's defined. MSE predictions speed. What is MSE? Maybe we find out further up. Predictions MSE, or you can also try the doc on MSE. Oh, there it is. MSE. It's actually a function we defined.
Yeah, the mean squared something.
Mean square error.
Mean squared error.
Mm-hmm.
We'll be able to apply the same approach for other more complex functions with more parameters, such as a neural net. So here, so we're not doing any learning here.
Correct, yeah. Correct.
And that was the whole stochastic gradient descent chapter, was that it's not a neural net. There's no learning, but it's still pretty good, or it can be good.
And I think we're just later we're just saying a neural net is essentially a couple of pieces of this whole thing, with some nonlinear functions thrown in between.
So here, we have torch, dot cat stack 3 stack 7s, and we're gonna view. This doesn't print it. Okay, so.
Oh yeah, it's not gonna. I disconnected the runtime here, so.
Okay, that's fine. So what I'm looking for. Okay, here we go with this. The weights and the biases. So what this is, so this weights, so parameters, the weights and the biases of model. The weights are W in the equation, the biases are the B in the equation. So the parameters, the W, this is the parameter, or calculating
The weights.
Or
Biases and parameters. Both of those.
oh, these are the
are
parameters. Okay.
Yeah.
And then
Weights
this.
and biases.
What did this equation? What was the equation? Actually, don't. It's fine. Because we kind of get more in depth down here. So you got your first linear function. We're
Weights.
getting into this like multiplication.
Mm-hmm.
So I'm trying to think like. So what I'm trying to get through all this is, what would we be replacing in this? Is it the ResNet? Is it this loss function? Is it both? Is it
I think it's the
optimization? Okay.
Or I understand that. I understand something, you know, with this, what we looked at towards the end, where we made this agglomeration of things. What was it called? Like we had a linear function, we had a non-linear function, we had another linear function, and it was wrapped up inside of this compiler thingy, and that replaced the neural net model. So that's something I understand to replace, because that's what we were doing in this other, like towards the end of that one. I guess the loss function is something we could replace, but that sounds more challenging to me, because I guess I understand less what's going on there.
Well, this is the MNIST loss. This is
correct. Like, so here we defined our loss function and then use the loss function we defined. So that's also something we could replace. And then I guess the optimization function we wouldn't replace. We would just use SGD.
Mm-hmm.
So yeah, loss function and model.
Okay. Is there a way to like bookmark or throw a marker somewhere here? Oops. To know where we are in Notebook? Can we highlight this somehow or no?
I mean, what you could do is you could put a heading there, then it would show up in the table of contents, and then you could click to get there.
Okay.
I did have to run it. So I guess you need to reconnect up there, top right. Or maybe you don't. Maybe you don't have to reconnect. Check out the table of contents when it shows up. There it is.
Yep. Okay, cool. Okay,
is it pretty smooth for you, or is it lagging a
No,
lot?
it's super, super laggy. But it's also like, I mean, remote control is never super smooth.
Right.
And if you've got you know,
a bunch of other stuff.
yeah, it's I'm not expecting it. And then also like anytime you open up the table of contents and you drop it in Colab, it decides to go like 16 lines down. Okay, so one problem with MNIST loss is currently defined is that it assumes that the predictions are always between 0 and 1. We need to ensure then that this is actually the case. Okay, so let's just keep that in mind. And then we have the sigmoid, which ensures it.
To do that, yeah.
Now
But that depends on what loss function you're defining, right? Like that's just for the MNIST loss function. We were expecting that everything is between 0 and 1, but that was the loss function we defined. Right, so for our loss function, depends on how we define it. So that define.
Are you saying that we don't necessarily need one that is between 0 and 1? Or
yeah, I think so. That's what I'm saying. At least from my understanding so far. Because it was just referring to the MNIST loss function, which is something that we wrote. So if we had written it differently, it might not have this assumption that everything is between 0 and 1, right?
Yeah, I think so, but also the concept or like the use of a sigmoid function is, from what I remember, widely used in machine learning.
Yeah. Mm-hmm.
So I think this between 0 and 1 is very common. So
totally.
I would kind of just apply it to the dog breed loss function instead of MNIST loss function, and then it's essentially the same thing. The way whatever we're calculating predictions.
So do you understand the MNIST loss function we defined up there?
I'm not entirely. I just wanted to find where it was, and then be like, okay, that's something that. So we need to. So that's kind of like my thinking, right? Is like, what are we replacing here? We're replacing the loss function. We're writing our own, and maybe that's all we have time for today. We're leaving the optimization
I was just thinking,
function.
I think we're maybe on the wrong project for this if the training takes so long.
Yeah,
like it's not something we can experiment around with much.
Right. Yeah, it's 32%. And
yeah, and it's on the first epoch, so I don't actually probably we should abort, or if we want to do anything, because this is not going to go anywhere, right?
Yeah.
I mean, if we want to quickly iterate and try out what's some different trainings result, then this is not the right project, simply, I think.
Yeah, so I think what might be interesting is like if we could keep the stream going and work through this, right?
This one. One of those.
And just write the function and then hit run and see. And then and then just let it run, do its thing. And then maybe we could write something nice for the forums of this is what we're doing, this is how we applied it, and then at least, in the timestamps for the YouTube video, we could get to this part.
Skip.
Yeah. If anybody's interested.
That's an option. Yeah.
So.
Or the other option is that we try this again using the OS desktop background classifier, because there we have a much smaller data set than here, which means that the training should go much quicker.
Okay. Is that all right? So you take full control if you want to stop this. And
no, I can't do it like so. The other one, it's not really cleaned up yet.
Okay.
That notebook, so I don't think it's like a quick switch that we could do right now. I'm just thinking of because I like this experimenting. I think this is interesting. This helps me understand a little more what's going on. So I think it's a fun thing to do. But I'm just saying maybe we do it next time and I clean up the the OS desktop thing.
Mm-hmm.
I don't know how much faster it would be though. So maybe we should let's do that. If you're up for doing that, then we could now go and check how much faster the training actually is.
Just to see like the default training, see how fast it is.
Right. Yeah.
Alright.
Yeah. So
Yeah.
that we see whether it makes sense as something to iterate on.
Okay. So
Yeah. Okay.
go ahead. You take full.
Alright.
You take control. See
I
what.
got it.
Yep.
Let's see. See if we can get there. No, don't do this. Yeah, you get one more chance. Otherwise, I'm gonna take the alternate route. Okay.
Look at Regs. Just sleeping on.
What's that? Such a good boy. Loading drive. It's a little slow. Call up notebooks. And wait, so I don't actually have it. Oh God. No, I think I have it in here. 1 second. Desktop stats here. Okay. Also, the pets dataset would work, of course.
That was just
The
cat
first
or
one.
dog, right?
Just that classifier.
Right.
That was pretty fast. Right? Let's try that instead. I think that should just, well, not dog breed.
I think that was in the intro, no?
Intro?
Yeah, I remember seeing a cat photo. Like yawning or something. Something super cute. So let's assume that this is really fast. Are we still thinking of working on this today, or are we?
No.
Okay. So.
No, we're just testing whether it's a good idea to do that next time, essentially.
Okay.
Because if this also takes long, then we got to think of something else. Then this iterating doesn't really make sense. But if it's fast, then I think it could be a fun lesson to go through for us.
Mm-hmm. Okay.
Okay. And then run all.
Super secret auth code.
Wow, so secret.
Yeah.
Such auth.
So yeah, I wonder like what you can do with that code if it really means anything, or what does it mean?
You need some sort of okay to access your drive. Okay, so this is untarring, and this is already running the learner. That's a quick one.
Mm-hmm. Yeah, ResNet 34.
Even so, it's running even a deep one. We could change that to 18. So yeah, that looks interesting. So now, let's actually try how fast it is if we do 18.
Yeah, just change learn to something else, and we could see the difference, like learn 18 or something.
Okay, so this is training now. How many?
Just one.
I don't think so. Really? I kind of
Well, I
remember
mean,
that there were more than one. Yeah, we'll
I
see.
thought it was also like 4, but I could be misremembering and thinking it was that we were running like the dog breed classifier. Was the dog breed classifier something that we thought of? Yeah, right? Because we found that, yeah, that's not in, right?
No. I think they're actually doing something like that later on. I'm not sure, but I had the feeling I saw something after we had, after we had done it already.
Right.
Okay, so it's running more than one epoch.
Yeah. But still, I mean, you know, relatively
That's
quickly, right? 34.
Much quicker than the other one, definitely, yeah.
Okay, so yeah,
So
then let's do this one.
Let's try the same thing that we did here, because maybe this is really long if we do something like that.
Yeah. So go back to the other one. What's happening here? Scroll up a little bit, because I don't think much is happening before this.
No, we just define this the function that knows how to label them. Label function. Then we do this get image files, which we just unveiled a little bit, which gets the images from that path where we downloaded the data set. And image data loaders from name function. That's a bit different. I don't know. I guess it just bundles up a couple of steps.
Yeah, I think that just like from the name of the directory or something like that.
Valid percentage seed. It's doing a couple of things in here. Oh, so this runs 2. Okay. Right? You're done. Okay, let's try doing the same thing. Is that CNN learner? Let's try doing the same thing with an 18. And then let's try doing this one, learn loss and optimization, learn low. Very descriptive naming going on here.
Yeah, I mean, that one you could say like loss, or I don't know, something with like the cross entropy or SGD or something like that. But right now it doesn't really matter. We'll clean it up later or off camera or something.
There is no off camera.
That's right. Learning is messy. Welcome.
This one's still running. I just figured before that as long as it's gray up there, you know, it's still running. If it's golden, then it's idle. So that's a nice way of knowing whether we should even check cool. Back there.
So scroll up. What was
47. It's not much difference. 51 seconds for the first epoch, 47 for the.
No, I'm looking at the valid loss, train loss, error rate.
16.9. So it's got a higher loss on the training, but a lower loss on the validation, and then overall a lower error rate on the deeper net. That makes sense. I don't know about the validation set. Wait, the training loss went down. Good. That makes sense. Okay, and here we got the second numbers. 58, training loss is still lower here. Lower here too. And
the error rate is
a bit higher. Interesting. Okay, so that took like 2 minutes each. That's decent. Like, so now if this one is similar, then we can totally do that.
So this is 4 though. You're doing 4 epochs.
Right, instead of 2. So should we try 2?
Yeah, I think 2, just because we're
comparing a bit.
Yeah. I don't know that we defined. Oh, error rate is something that's predefined, I think, right? Metrics, error rate. Yeah. Yeah. Okay.
These are all, we're all using stuff. Okay, this one's still going on. How far ahead are you? Oh, it's still on the, yeah.
Still on the first.
Still on the first epoch, yeah. That's,
Yeah.
I'm just gonna stop it, okay? Or do you want to actually
I don't think we're
know
gonna.
what it is?
I don't think this will finish before we finish the stream.
Right, yeah. So
you can go ahead, stop it.
yeah. Bye. 29 minutes. That brings up memories from our first stream.
Yep.
Oh yeah, look at it, it's red if it errors. Infinity red.
Okay, so 46 seconds with an error rate.
Again, very similar. Okay, and so yeah, what's the 0.7, 0.16, that's much lower. 0.13, also lower. And error rate 0.07, that's higher. Interesting. So strange, huh? What makes this? How are they connected? Oh, I mean, we learned that the loss and the metric isn't necessarily entirely correlated, right? Like, it must be somehow correlated, but it's not what we're. Okay, 0.06. So this got better, 0.0. Huh, the second one had a worse error
like
rate. Should be going up.
The first one, or the ResNet 30, was that 34, 32?
36.
34.
34, you're right. Yeah.
That seemed to be the best.
How do you, like, what are you basing this on?
So
like, these are our the second values, 0. It's kind of hard to compare like this.
Yeah, so that's supposed to be the lowest, right? The 0. Yeah, it is.
I'm just gonna put them all into one thing.
I'll let you clean it up.
Just looking, I'm just taking the last ones now. Okay, so this was the first one. I don't know, 50, whatever.
Doesn't matter.
So this was the 32, 34. Res 34. And this was res 18. And then we have this one with the loss, ResNet 18 also. Epoch 0. Why is the other ones both said still epoch 0? This is something else.
Yeah.
Look at that. Here we're in this two we're actually only running one epoch, but we're running it twice.
Yeah, I wonder what's happening there.
And we're doing different things, it seems.
So do you want to keep it consistent with the first one? Or
this one?
Or are we just like, at this point, we're not even comparing apples to apples anymore?
It might be, yeah.
You know?
Like, these two are the same maybe to compare, but this is maybe something else.
Okay, so let's look at this ResNet 34 and 18 for a second, right? We have 58, and so the training loss is lower in 18. The valid loss is lower, and the error rate is higher. And then
interesting, huh? I don't know.
And then just to, you know what, copy that second epoch. The first, right, the second one. Or the first one.
From here?
Yeah, either one. Whatever, let's look at that one because it's the most, it's run through this whole thing. Sure. So that one's actually kind of...
I'm disturbed by not having the last number here. All right.
Okay, so the training loss is a bit lower, even more. The
validation loss is a little higher, but lower than the first one.
Than the first one, and then that is.
This is in between.
In between. So interesting. So the second two values are in between the first.
First one is lower.
The first two.
Yeah, I feel like we definitely gotta have to understand what does this mean that this is running 2 times with epoch 0?
So I think if you
This
just
is,
did,
must be inside of fine tune, huh?
yeah, I think if we did fine tune 2, like we're doing, right?
Uh-huh. You're right. Yeah. Uh-huh.
You know.
Yeah, I believe you're right.
So why? I mean, since it's so quick, why don't we just do 2 there,
Yeah.
run it, and then since we're doing ResNet 18 in our, like, you know, sort of custom one anyway, let's just, yeah, whatever, override
Wait,
learn 18.
did you mean something else or this one?
No, this one's fine. Yeah.
Yeah. Okay.
So the last here, I could also. No, I don't have remote control anymore.
You don't? Oh,
I do not.
there you go. Don't be sad. Okay.
And then
2. Where's 1, 2? No, that's confusing.
just to keep it the same spacing.
Wait, can you put an underscore in there so that it's
Okay,
connected and knows what it's? Yeah, thank you.
All right.
The important things.
So these 2 were running just 1 epoch, and these were running 2.
Correct.
So, yeah, when this is finished, then we'll see.
Wait, but again, it just says epoch 0, and then so maybe this is. I thought it was stacking them together in the other ones.
I think we have to look at what. So hold on. So this is fine tune, and then up here we did learn loss dot fit.
Yeah, we're gonna have to look into this a bit more. What do they actually do? This different fitting, fine tuning. They clearly do different things. Look, we got again epoch 0, epoch 0.
I think it's just gonna do
4 times epoch 0.
I don't know. Oops.
Fun. Learn.fun.
So here we did get epoch 1. And
the first time not, but then yes. Strange.
I'm just gonna run this as well.
So it does some fine tune, seems to be doing something beforehand, before actually fitting, right?
That's what I'm hoping to see with running the same function, but with fit versus fine tune. Maybe we'll get similar results. I don't know. But this, oh no, this only did 0. It didn't have like the preliminary or this epoch. I really do wonder what this one is. But anyway, let's look at it. So
there was something, I think there was something about that it's taking, that it's first training. I think he was talking about that actually in the lecture, in the first lecture, about how this fine tune does something specific.
So this here, this fine tune twice, I mean, as we can expect, it is so far the best one. So I actually think that so we could see what the potential, and then Oh, wow.
All right, it started really high. Fit. So yeah, fine tune. Interesting.
Come on, there we go.
Oh, yeah, I get it.
Okay.
Mm-hmm.
I mean, this is also like super messy, but so even on this one, the second, so this fine tune is like leaps and bounds better than the fit in this case. So I think fine tune is probably doing some sort of magic.
Yeah, I think it's something about that it translates. I mean, that's just transfer learning, but I think it's something similar to that. It takes something from a pre-trained thing and applies it.
Yeah.
I mean, that's transfer learning in general. So maybe I'm just mixing these things together. I don't know. Okay, this is fun. Let's.
But just one last thing. What's interesting too is because like the fine tune one worked well on. These were all fine tuned. These three were using fit. However, this one we applied the loss function to as well, and the optimization function. So I think
that was pretty good.
Yeah, and this is pretty on par, I would say, with these, right?
Right.
Yeah, this is very close to this, and 14 very close to 17, whatever. So I think fine tune is. I'm sure we could just look in the documentation, but I think it is applying these optimization and loss functions to it somehow. Cool.
And maybe it has like some good predefined loss function.
Yeah. So then, so I guess let's make a note for Monday. We can look into what fine tune's actually doing, and that could be just as an understanding. Nice. Just to understand what fine tune is doing, and then let's define and then let's define our own loss function as well. So look into what fine tune's doing, define our own loss function. And then if we have time, begin peeling apart the layers of this like ResNet 18. What is it actually doing, and start maybe build our own ResNet or deep learning function.
Yeah. Okay, makes sense.
Cool. All right, and this will be on Monday.
Yeah.
Cool. This was productive.
Great.
This was fun. This was nice. A nice little review, and this was nice.
And it's helpful. Yeah, I think it helps us understand a bit more of the basics or like the background of this. Cool.
All right. Cool. So let's end the stream, and we'll see everybody on Monday.
Bye-bye.
All right. Bye-bye.